The most extreme objects in the universe might not be black holes or neutron stars, but something we have never seen and may already have photographed without realizing it. When the James Webb Space Telescope stared into the early universe, it found galaxies that looked too big, too bright, and too mature for their age. Some of those little red dots are so luminous that if our standard model is right, they simply should not exist a few 100 million years after the Big Bang. To explain them, some physicists have revived a wild idea: dark stars. A dark star sounds like an oxymoron. Stars shine, darkness doesn't. But in this hypothesis, the darkness is not the absence of light. It is dark matter itself, powering a star that glows not from nuclear fusion, but from the annihilation of invisible particles in its core. To see why this is radical, we need to rewind to the first stars. In the standard picture, a few 100 million years after the Big Bang, gravity began pulling together tiny overdensities of hydrogen and helium gas. As these clouds collapsed, they heated up. When the core reached around 10 million degrees Celsius, hydrogen nuclei fused into helium, releasing energy. That ignition created population 3 stars, the first generation made almost entirely of pristine hydrogen and helium, with no heavier elements. These primordial stars were expected to be monsters, hundreds of times the mass of the Sun, burning hot and blue, living fast and dying young in titanic supernovae that seeded the universe with heavier elements. Dark stars take that story and insert dark matter at the crucial moment. In the early universe, dark matter was not just a distant halo around galaxies, it was densest in the same regions where gas was collapsing. If dark matter is made of particles that can annihilate with each other, like many WIMP models predict, then wherever the density is high, they release energy. Imagine a forming protostar at the center of a dark matter cusp. As gas falls in, dark matter also piles up. Annihilations in that dense core inject heat into the gas. If this heating is strong enough, it can counteract gravity and puff the star up, preventing it from contracting to the tiny, dense state needed to ignite fusion. The result is bizarre. A star that is enormous and relatively cool on the surface, but powered from within by invisible particle physics. Calculations suggest dark stars could swell to tens of astronomical units, across larger than the orbit of Saturn, while containing up to 1 million solar masses of gas and dark matter. Because they are so bloated, their surface temperatures would be more like a red giant than a blue supergiant, emitting most of their light in the infrared. That makes them perfect targets for JWST, which is optimized for infrared wavelengths. A single dark star could be as bright as an entire small galaxy, yet be just one object. Some of JWST's brightest, most distant red sources might not be galaxies at all. They could be individual dark stars masquerading as compact galaxies at the edge of time. This is not just hand-waving. Teams have taken candidate JWST objects and asked, if this were a dark star, what would its spectrum look like? A spectrum is like a barcode of light, showing how bright an object is at each wavelength. Normal galaxies show a mix of starlight and gas emission lines. A single huge star would have a smoother, more stellar-like spectrum. Intriguingly, a few of JWST's little red dots can be fit by dark star models as well as, or sometimes better than, by standard galaxy models. The fits are not yet conclusive, the data are noisy, and gravitational lensing can magnify and distort what we see. But the possibility is serious enough that people are writing detailed papers about JWST dark star candidates. If even one of these objects turns out to be a genuine dark star, it would be a double discovery. A new kind of astrophysical object and direct evidence that dark matter can annihilate and heat normal matter. But dark stars are only one piece of a bigger puzzle. JWST has also found what some call red and blue monster galaxies. In the early universe, the red monsters are massive, compact, and already full of old, evolved stars when the universe was less than 1 billion years old. The blue monsters are intensely star-forming, converting gas into stars at rates hundreds of times higher than the Milky Way. In the standard LCDM cosmology, that is, cold dark matter plus a cosmological constant, structure grows hierarchically. Small things form first, then merge to build bigger galaxies. That process takes time. Simulations like Illustris and Eagle, which implement this physics in supercomputers, do produce big galaxies early, but not as many or as massive as JWST seems to be seeing. To match some JWST counts, you either need galaxies to form stars far more efficiently than expected, or you need dark matter to clump earlier and more strongly than our current models allow. This tension has been called a cosmology crisis, sometimes a bit too dramatically. We should be cautious. Early JWST results relied on photometric redshifts, which estimate distance from colors, and those can be fooled by dust or unusual spectra. As more spectroscopic redshifts come in, precise distances measured from spectral lines, some of the most extreme claims have softened. Still, even with better data, a pattern remains. The early universe appears surprisingly busy. Massive black holes of 1 billion solar masses are already in place within 700 million years. Stellar populations look older than the cosmic clock seems to allow, and the ratio of stellar mass to halo mass in some systems looks uncomfortably high. There are 3 broad ways to respond. 1. Our astrophysics of how gas cools, fragments, and turns into stars is missing some efficient pathways. 2. Our understanding of dark matter and its clustering is incomplete. 3. The underlying cosmological model, the expansion history itself, needs revision. Option 1 is the least revolutionary. Maybe primordial gas cooled faster thanks to molecular hydrogen or early metals from a first unseen generation of tiny stars. Maybe feedback from supernovae and black holes behaved differently at low metallicity, letting galaxies hold on to more gas. These are messy, non-linear processes. Small changes can have big effects. Option 2 tweaks the dark sector. If dark matter is slightly warm instead of perfectly cold, or if it has self-interactions, the timing and scale of structure formation can shift. Some models even propose an early burst of dark energy that briefly accelerates expansion, changing when and how halos collapse. Option 3 is the most dramatic. Perhaps the Lau in Lau CDM, the cosmological constant, is not constant. Or perhaps general relativity itself needs modification on cosmic scales. These ideas are being explored, but they must also fit everything else we know. The cosmic microwave background, baryon acoustic oscillations, gravitational lensing, and more. Any new model has to pass a gauntlet of precision tests. In this context, dark stars are like a stress test for our imagination. They show how particle physics, cosmology, and astrophysics can intertwine in unexpected ways. A tiny change in the properties of dark matter, giving it an annihilation cross-section in the right range, could reshape the entire story of the first luminous objects. If dark stars existed, they would eventually die when their dark matter fuel runs out or is depleted from the core. Then they could collapse into massive black holes, providing the seeds for the supermassive black holes we see at the centers of early galaxies. That would elegantly solve another JWST puzzle. How to grow billion solar mass black holes so quickly without violating the Eddington limit, the balance between gravity pulling in and radiation pushing out. In that sense, dark stars are not just exotic curiosities. They are potential missing chapters in the biography of galaxies, black holes, and maybe even life, because they would influence when and where the first heavy elements are forged. Whether or not dark stars are real, JWST has done something profound. It has pushed our standard model of cosmology into a regime where its predictions are genuinely being strained. This is exactly what a good theory should face. Precise, uncomfortable tests at the edge of its domain. We may find that clever, conventional astrophysics explains most of the anomalies. We may discover that dark matter is richer than a single cold, collisionless particle. Or we may be standing at the threshold of a deeper revision, where the neat LAM-CDM picture is just the low-energy approximation of something stranger. For now, every new deep-field JWST releases is not just a pretty image. It is a data-rich argument with our best ideas about space, time, and matter. And the universe is answering in a language we are only beginning to decode. And as we follow that conversation further, the next surprise may come not from what JWST sees, but from how we learn to listen to the cosmos in entirely new ways.